All right, so today we are going to continue our discussion on modern processors. So last lecture we talk about, well, in theory, as what we learned before is that an instruction is ready to execute if the instruction has completed its own work in the current stage and no other instruction is occupying the stage and all its input is ready, right? So in theory, whenever an instruction is decoded, whenever the inputs are ready, meaning that all data dependencies are resolved and the target functional units isn't available, we should be able to execute this instruction. However, because our pipeline design kind of like restricts us to execute this instruction in order, so we cannot really do this as whenever an instruction is ready to execute. In addition, if you look at the register, because the instruction set architecture only give the limited number of registers for the compiler to generate your code. So it turns out that in addition to the true dependencies that we have in black arrows on this data flow, this data dependency graph, we also have those red and blue arrows, meaning that we have dependencies that are false in a way that we cannot reorder this instruction because if you do this, you may overwrite a result that will be used by another instruction. So that all restrict our capability in executing an instruction whenever it's ready. So imagine this. This is like this is but if you look at the scheduling, if you can change the scheduling policy a little bit in this way, like, okay, what if I change, what if I give each instruction a new output register? Then it turns out that all the data dependency will be eliminated, right? All the false dependencies will be eliminated. So that comes up with the idea that called register renaming. So the basic idea of register renaming is that we make architectural register again as an abstraction, and dynamically the processor would remap those architectural register to the physical register that are in use. And whenever we see the physical registers are with their value are ready, we can just have the instruction values to go ahead and execute. So that's the basic idea of register renaming. And to support register renaming, our processor pipeline will be no more the stage, will be no more within a 5-stage. So after the instruction fetch and decode, we will have a renaming logic. And the renaming logic is basically the mapping between the architectural register and the physical registers. And in modern architecture, your processor will probably have 64 to 128 physical registers for you to use during the instruction execution. And after you rename these instructions, those instructions will be put into the instruction queue. And whenever the physical register value is ready, it will inform the instruction queue to put an instruction to execution in each of the in one of the pipeline that's shown below. So if it's an integer instruction, it should use LU. If it's a floating point, it will go to the floating point unit. If it's a branch, we will have a branch unit. If it's an address, if it's a memory instruction, it will first go to address resolution and low store queue for memory accesses. And whenever your value is ready, you just update the physical register file, and the physical register will inform or trigger the execution of an instruction in the instruction queue again. So that's the basic idea of register renaming. And because register renaming is just a technique, we eliminate all the all the false dependencies. So after register renaming, you are only seeing true dependencies in your code. So in this way, you can imagine your processor is now completely scheduling your instruction whenever the data dependency is resolved. So in this way, the scheduling or how many cycles it takes to empty out the pipeline, it becomes relatively straightforward in a way that you just look at the data flow graph and you are able to know how many cycles you need to execute all the instructions. So for this pieces of code, each cycle we are going to receive a new instruction from the renaming logic. So in the very first cycle, we know the first instruction is ready to execute. However, in the second cycle, we know the second instruction needs to wait for the outcome from the first instruction. And the first instruction, because it's a 4 cycles to get its result broadcasted to the second instruction. So that's why we put an arrow here that is 4 cycles away from the first instruction. And the third instruction, if you look at the dependency, it's still depending on the output of the second instruction. So that's why we have an arrow here. And for the fourth cycle, we finally got a fourth instruction that is not depending on 1, 2, 3. So it can put into execution immediately. So if you keep drawing this, you will figure out, wow, it takes a total of 12 cycles to issue all these instructions. Now, we always want our execution to be better. So we start to have this idea called superscalar. So the superscalar is that, well, since we have more functional units, like you have seen in the previous graph, right? The processor has more than 1 unit. So it's highly possible that if we can decode more instruction decode and rename instruction, more instruction at the same time, it's highly possible that you can find more instruction like a memory, like an integer, like a branch to execute together at the same time. So so that's the idea of superscalar. So you can imagine with superscalar processor, your pipeline will be something like this. So your branch predictor will help you to know what instruction to fetch and what instruction. And then after you fetch the instruction, you still decode it, you rename it, issue it. However, superscalar means that you can fetch multiple. And for example, if you have a two-way superscalar, it means that the fetch unit, the decode unit, the renaming logic, they all support 2 instruction execution at a time. And when we say 4-way superscalar, it means that these units are timed by 4. And with this, you can imagine, well, each cycle you are going to receive more instructions that are available for you to schedule, and potentially you are going to have better capability to reorder your instructions. So if you have these pieces of a code, you would well, wait, okay. If you have the same pieces of a code, right? And right now I said it's two-way superscalar processor. You can imagine cycle, we are going to get 2 instructions at the same time. So like in the first cycle, we got 1 and 2 renamed. And if you look at data dependency of 1 and 2, yes, there is a data dependency. And in the next cycle, we get them into our instruction queue. And you look at the data dependency, you will figure out that, well, 3 is still depending on 2. However, for 4, you right now making it execute earlier. And if you keep filling the graph, you will figure out like in the next cycle, you got 5 and 6, although they are not ready to execute, but in the next cycle, they will be able to execute. And if you get 7 and 8, you will figure out it's going to be later, and 9 and 10 at this point, right? So so after drawing this data flow graph for a superscalar processor, you will figure out previously we need 12 cycles to get all the instructions executed, but right now you only need 10. So if you can fill it, you will figure out that, well, 10 instructions take 10 cycles, so the average CPI would be 1 now, right? So that's the superscalar execution. So right now, and with the superscalar pipeline, as I mentioned, right, you can imagine the modern processor is actually having a decoupled front end and a back end. And the front end means that the interface between your software and hardware, well, sorry, between your memory and your your processor in terms of fetching, decoding, and renaming instruction. And the backend is the actual pipeline that you are executing instructions. So those are decoupled. And we will, and well, however, even with this kind of advanced pipeline, if you don't design your code carefully, or if you write code that are just not so friendly to the modern processor pipeline, even though you have super scalar, it doesn't help. So an example that I can give you here is linked list. So linked list is notoriously bad for performance because, as you can see, the data dependency really kills the performance. And even though you have super scalar, these pieces of code still cannot be complete earlier, right? Okay, so and another issue that some of you already identify is that, well, for this kind of code, right, uh, like the branch, it takes a lot of time to resolve. And what if the branch is mispredicted, right? And at this meantime, in the meantime, you also know that instruction 8 already finished its execution. And if branch 6 is mispredicted, it means that every instruction that is after 6 should not have its value presented. So A should be flushed, but since A finished, there's no way we can revert this execution. So there is a bug in this processor. So how we, and the other thing, and that branch prediction is not the only issue. And as you learned before, probably like in arithmetic operations, you might have like exceptions, like floating point exceptions, divided by 0 exceptions, or overflow that you need to address, right? And whenever you have an exception, you have to jump to a pieces of exception handler, which is a different function. You have to change your program counter. So your execution flow is going to be different and than expected. And there are also other exceptions, like when we perform memory accesses. What if you have a page fault, as we just mentioned in a lecture of virtual memory, that, well, the page that you are looking for is not found in the main memory? Then you need the operating system to handle the address translation, to handle the mapping of your data. So that's not so both are going to change your execution flow. So what if this exception occurs during your instruction? And sometimes because you already get some later instruction executed in the pipeline that I just showed you, so your code will lead to incorrect result. So one thing I want to say is that, well, it seems like the previous pipeline works fine. However, it's a buggy pipeline. So how to fix the bug is what we are going to talk about today. And the solution is reorder buffer speculative execution. And however, with reorder buffer speculative execution, we are still underutilizing our pipeline. And so that's why we need simultaneous multi-threading. And later on, we are going to talk about this processor. They are too power consuming. So we need chip multiprocessor to give us a balance between power consumption and performance. But now let's talk about reorder buffer and speculative execution. So as we said, right, if an instruction is executed out of order, it means that there is a potential that it may be canceled at any time. So so we need some kind of mechanism in our processor to revert that execution, to flush its result, revert the architectural states it has changed. So in this way, we create a new execution status called speculative execution. So by speculative execution, it means that we just guess this instruction will be executed. However, and we allow this instruction to go to its execution stage and propagate its result to later instructions. However, because this instruction may be canceled anytime, so you need to have you need to be prepared that we have to restore the status before it's executed. So under the status, an instruction is executed in speculative mode. So, so this is called speculative execution. So the mechanism to support speculative execution is reorder buffer. And reorder buffer is a buffer that keeps track of the program order of instructions. So if you think about, if you try to remind yourself regarding the pipeline, the single issue 5-stage pipeline we have, we never have to worry about the speculative execution because, well, the branch is resolved in its execution stage, and because the branch is blocked in its execution stage, so all the instruction after the branch will never enter their execution stage. So you never have to worry about value being changed. However, because we have out of order execution right now, so an instruction that is later than a branch instruction may end up be executed earlier than a branch. So the whole thing here is that you just cannot let an instruction change the final architectural states before the branch is resolved, or an instruction pass its exception, potential exception stage. So so the basic idea of reorder buffer is that, well, we just need to know the order of instruction and make sure that an instruction that is later than the branch is never going to be commit or say present its result to the rest of the world. By the rest of the world, I mean outside the processor, or say change its architectural states before a priori instruction, including a branch instruction finished. So that's the basic idea of reorder buffer. So the reorder buffer, so you can imagine when your instruction enter the instruction queue, the reorder buffer is actually is right now a combined unit between of the instruction queue that whenever your instruction enter the instruction queue, you will give the instruction an order, or say like a number, and this number represent the order in its original program. And the instruction can only be considered as finished if all the priori instructions are finished. On the other hand, if there is an instruction priori to this instruction is not yet finished, the processor should still have to keep its result in private, not making it public. And if a priori instruction of the instruction failed, meaning that the branch is mispredicted, then this instruction will have to exit its reorder buffer entry. And before you're doing that, you have to restore all your architectural changes, and namely the register values. So that's the basic idea of reorder buffer and commit stage. So let's look at how it works in our 2-issue register renaming processor. And because it's a buffer and it's a reorder buffer, and you have to maintain the order. So right now, you should imagine our instruction queue is right now a circular queue, and you have a head, you have a tail. So the first cycle, we rename 2 instructions, and you know these 2 instructions, they have a dependency. And in the next cycle, as we previously learned, the 4th instruction after rename, it should be executed immediately because there's no dependency between the 4th instruction and the previous 3. So in the next cycle, and the 1st instruction can also be executed. So in the 4th cycle, you can see the 4th instruction is right now in execution together with instruction 1. However, instruction 2 and 3, they have to wait for the result of the lower instruction to come up. And then after the fourth instruction commits its value, write back its value, instead of letting this instruction go, leave the pipeline, we put this instruction in commit stage. But in the meantime, we make the data forwarding available in a way that if the fourth instruction, if there's anyone depending on the fourth instruction execution, mainly here, the branch instruction right now, it can execute. And when a branch resolve, if any of the following instruction turns out that, well, if we are not taking a loop, for example, if instead of executing 6 to 10, we want to execute other instructions, then all these instructions, they will be flushed and they will not be commit. However, if the branch prediction is accurate, we can keep executing those instructions. And as you can see, the fourth instruction, it will stay in the pipeline until the previous instruction, means the third instruction, finishes execution. So in this way, if there is an exception happens here, we will have the capability to flush all the rest of the instructions. So that's the basic idea of having reorder buffer and a speculative execution. And at this point, you can see that once the commit is in order, so present to the outside of the world, you still have an illusion that all my instructions, they are completed in order. So that's the whole idea of register renaming pipeline. So right now, I want to ask you this. So for this pieces of a code, what's the average, how many cycles it takes to issue all instructions? All right. 10 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so according to your votes, it looks like there is not really an answer that is dominating. So we need to go to discussion. And I saw some of you saying that, well, in your group, most people are quiet, but there are also cases that people saying that you learn a lot from your group. So what really makes the peer instruction or the breakout room discussion works is that you guys really have to speak up for yourself. All right, so right now, I do encourage you guys to open the question that I sent you and try to discuss as much as possible with your group members. Let's go ahead and do it. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so right now, can I invite some of you to share your thoughts with us? Okay, Byron.
Hey.
Hey, what do you think, or what does your group think?
So we first started off with saying that 1 and 2 were safe to execute in the beginning.
Okay,
And
because after rename, they actually do not have any data dependency, right?
yeah, there's no
Okay,
dependency.
so 1 and 2.
Yep. But 3 and 4 are then dependent on 1 and 2. So we're going to wait for that. So in the next cycle, we're going to run 5 and 6, which are the equivalent
Okay,
1 and 2
so
from the
so
next
3
one.
and 4, so it will, so let's see, this is 1 cycle, this is 2 cycle, this is 3 cycle, this is 4 cycle. So I would say like 3. Oh, okay, 1, 2, 3. It takes 3 cycles to get its result. So
Yeah.
the 3 should be somewhere like
There.
this,
Yeah.
right?
And then the 4 should be on the above one. The
Okay, for 4 because it takes
because it's 2
okay,
cycles for an integer, for an add.
okay. So 4 will be here. Okay.
Yep.
So
And
5
then
and 6.
yeah, 5 and 6 can run on the second like clock
So
cycle.
5, are you sure we can execute it?
No, so we're gonna have to rename those to
Yeah, but for 5, right, there is a dependency here.
oh
Didn't you see that?
you're
So
right.
we may have to wait here, right?
Yeah.
And
Okay.
then we would have, who else is depending on 6? 7 is depending on 6, right?
Yeah. And so is 8.
So, okay. So that would be 6, right?
Yeah.
And so is 8, right?
Yeah.
So if you draw the data flow diagram, you will figure out that, wow, it takes, it actually would look like this, right? So it takes about like a total, so here I think, well, you guys assume that the LU would take 2 cycles, right? So which I didn't clarify in this question. So that would be 8, right? In this way, right?
Yeah.
Okay, so cool. So looks like after discussion, most of you got the idea. All right, so if you look at this, right, you will figure out that the addition of reorder buffer doesn't actually change the way how you schedule the instruction, right? So that's why we said you can consider the pipeline right now is decoupled. It has a decoupled front end and back end, in which your front end is just keep feeding instruction and scheduling instruction, and the backend is trying to digest those instructions, right? So, and the backend, as long as you have unlimited or say big enough reorder buffer, it shouldn't affect your front end performance. So that's but reorder buffer also help us to solve the issue of exceptions and branch predictions. So so if you look at the pipeline of modern processors, the pipeline of modern processors, if you look at that, right? Look, this is Pentium 4, which is a processor about 20 years ago, and its front end has a branch target buffer. You probably know the BTB is what, right? So this part is like the branch prediction, and with the branch prediction, we have the instruction fetch, instruction decoder, we have a trace cache, and here you see there's a micro up. So let me explain a little bit here is because right now, although x86 processors, they still present an illusion that it's a 6 instruction set architecture processor, and indeed the front end, this part and this part, they all support those 6 instructions. However, the instruction decoder in Intel processor or AMD processor, they would actually make an x86 instruction into several RISC processor-like micro operations here. So so that's why we keep saying that the instruction fetch unit, decoding unit, they are like the front end of the processor, because the backend pipeline, it doesn't really differ that much in RISC processor and Intel processor or AMD processor now. They are all pipeline RISC-based processor. So so it doesn't really matter. So the performance of the processor doesn't really matter that much as long as your pipeline design is elegant and efficient. However, Intel and AMD, they have tons of patents in their pipeline design. And plus, Intel has very good process technology. So that's why Intel can keep the crown of, or AMD can keep the crown of high performance computing now, even though for now. So although we see there's a raise of the market share of ARM processor, but if you look at the market share that AMD or ARM grab from Intel, they are actually the market segment that's not so profitable in Intel business. However, on the other hand, for those mobile devices or small devices, they deeply relying on the data center server provide their services, and those data center servers, they all use high-end Intel processors because only those Intel processors can give their the desired performance. And but on the other hand, right? So if you just learn from the textbook, you will feel like CISC design is not efficient. However, how they really make it efficient is because right now in their front end, they have the decoder. They modify the instruction decoder to create RISC-like instructions internally. So the rest part, or say the back end of the processor, is a RISC processor. It's like ARM or better than ARM. Okay, so right now, if you look at the pipeline, this is register renammer, so you know who they are. And you have a micro op queue, which is the instruction queue. You also have a memory instruction queue, and they have the memory scheduler. And here you have the instruction scheduler that would schedule instruction into corresponding ALUs or address calculation unit. And for floating point, they have their own register bypass logic. And here you can see there is also like a data bypassing logic. And there is also L2 cache. There is there's a trace cache. Is actually well. So here is the trace cache. The trace cache is the instruction cache of pendant 4, and this is the L1 cache, data cache. See, after you learn this computer architecture class, you know what this graph is talking about, and almost every turn you see here, you learned, right? So that's one you should feel proud of yourself, because right now, wow, I can explain this to the general audience, the internal design of an Intel processor. So that pendant 4 is like a grandfather of processor. So let's look at the Skylake processor, which is closer to the processor, the Core i7 processor that you are using now. And it's still not too different in a way that we still have the micro ops and the iCache. It also have the micro ops, and you have the instruction cache, and you have the decoding pipeline, and you have the branch prediction unit that helps you to figure out what's the next instruction to fetch. So that's a front end of Intel processor. You still have the L2 cache, L1 cache, and then after you decode instruction, you have instruction queue, unified instruction queue instead of a separate queue like the pendant 4. And then we have the renaming logic, we have the retirement logic, and the retirement logic is actually the commit logic. So it's essentially implementing the reorder buffer, and the scheduler is the issue stage, as we mentioned. And again, they have the integer pipeline, 4 integer pipeline, and load store 2 load. Let me see. They have 2 load unit and 4 store pipeline that goes to that interact with the data cache. So that's the Skylake design. So, and this is a Sandy Bridge, even newer Intel architecture. And as you can see, it's still not too different. You have the branch prediction, interact with your cache, have the decoder so this pre-decoder is decoding your x86 instruction into micro ops. And this instruction queue, it gets another decoder which try to decode it to an even lower level instruction. And you have another micro op cache, and you have the allocator renaming retirement logic is like the instruction queue plus the reorder buffer. And then you have the scheduling, go to different pipeline. You have the L2, L1 cache, and the memory controller. So that's the Intel processor, the modern Intel processor, right? So it's not too different from what you just learned from us. And this is the AMD processor. And as you can see, it's still the same. You have the branch prediction, and the branch prediction, it has, well, for AMD, it has larger I cache, but it's only 4-way. And after you fetch an instruction, you decode it. And again, after you decode it, it will be in the micro op queue. And this micro op is equivalent to, well, it's a different micro op instruction set architecture, but it's the same concept. You just decode or say rewrite your x86 code into the micro ops like RISC instructions inside this processor pipeline. And again, they also have register renaming unit for floating point and the integer, and they have their own scheduler into different pipelines. And the AMD processor, they have larger L2 cache. However, if you look at their L1 cache, it's also 32K 8-way. And the reason of doing that, you probably already learned, is because we want to do virtually indexed, physically tagged cache efficiently. So that's the AMD architecture. So they are not too different, right? Look at the design. Almost every modern processor contains the knowledge that you just learned from these 2 lectures. Okay, so however, right, if that's the pipeline that we are living with, look at linked list, right? Look at this linked list. We will waste a lot of slots in using our pipeline. So the instruction level parallelism means the amount of instructions that you can execute at the same time will be really low. So that comes with another idea called simultaneous multithreading that's incorporated into modern processor pipeline. And simultaneous multithreading is actually invented by Professor Ding Townsend in the UCSD CSE department, and he is also my advisor. So if you ever see this face in the CSE department, CSE building, yes, he is the person who invented simultaneous multithreading. And simultaneous multithreading is one of the technology that has been tightly incorporated in both Intel and AMD processor. So let's look at the concept of simultaneous multithreading now. So simultaneous multithreading is that, well, if you look at the previous graph that I just showed you, right? For linked list, if your program just looks like this, there's no way that you can squeeze more parallelism inside your processor. As I just showed you, even though I improve the issue width or say the fetch width to 2, it makes no improvement. So for this pieces of code, you are going to waste a lot of your hardware resource. So the basic idea of hardware of simultaneous multithreading, since we are going to waste the hardware resource anyway, why don't we just make this hardware resource available for other programs? So in this way, a processor can use instructions from another thread or say another process. So here, although we say threads, however, it's different from the concept of threads in operating system. It doesn't necessarily mean the thread that share the same memory space as you learned in operating system. It could refer to another process. So that's why I put process here. So you fetch instruction from another running program to fill the not utilized part of your pipeline. So in this way, you are sharing your resource with another program. So that's the idea of simultaneous multithreading. So the basic idea of simultaneous multithreading is that, well, if this program cannot fully utilize the pipeline, let's just have another program running together. So if you look at, but to support this, your processor must have the capability to fetch instructions from two processes at the same time. So right now, the instruction queue, even though we have the capability to fetch 4 instructions, we probably need to share that with another thread. However, it's probably not a big issue because if you look at the linked list example, no matter how many instructions that you can fetch at the same time, you just cannot use this, right? So let's just fetch 2 instructions from one thread, 2 other from the other thread. And as you can see here, right now we assume this processor still only have the capability to execute 2 instructions at the same time. Well, the first cycle, we will schedule the first 2 instructions from the left-hand side. However, the next cycle, we fetch 3 and 4, and we figure out that we cannot do anything to 3 and 4. So why don't we just put the first instruction and the second instruction from the other thread into execution? And in the meantime, we also fetch 3 and 4 from another thread. And when we fetch 6 and 5, you start to figure out for 6 and 5, well, 5 can be executed immediately. However, we still only use one of the functional unit in this simultaneous multi-threading processor. Let's try to see if there are other opportunities. However, unfortunately, at this time, we know 3 and 4 in the other thread, they have dependencies with the load instruction. And for this guy, it has dependency with this instruction. So we cannot execute 3 and 4 immediately. However, in the next cycle, we know 4 and 5 that will be able to execute from this thread. However, on the left-hand side, there's nothing we can do, right? So if you look at the next cycle, we get more. If we keep going on, we'll figure whether the first linked list example has nothing to do. The right-hand side can always help us to fill in the unutilized part of the pipeline. So that's the power of simultaneous multi-threading. So the basic idea is that since one process would not be able to use all the resources you have, why don't we just share it with another process? So that's a basic idea of simultaneous multi-threading. So look at that. The cost of simultaneous multi-threading is actually not that high. So this is the super scalar pipeline that we just have. And for simultaneous multi-threading, you just need to double your fetch unit. And probably don't need to double your fetch unit if you want to share them, right? So all you need to do is that you just have 2 sets of program counter. So you know like the progress of each program. And then the fetch decode unit and the instruction cache, they are all shared. And you just need 2 register renaming table so that you know like the architectural register of program 1 is now where, right? So that's all you need to support simultaneous multi-threading. And on average, it takes less than 5% of the die area to support simultaneous multi-threading, but you get the benefit of use unutilized part of your pipeline. So that's why Intel and AMD, they all adapted the idea of simultaneous multi-threading. And Intel actually started using this idea since Pentium 4, which is about 20 years ago. And AMD can only start using this idea in recent years because this project was actually done by Ding Taozhen when he did his internship in Intel labs when he was still a PhD student. So so Intel owned a patent of simultaneous multi-threading, and it registered a trademark called hyper-threading. So nobody else can use that. But because like for each patent there's a 15-year expiration. So after this patent get expired, AMD can finally build simultaneous multi-threading processor. So previously, only Intel built simultaneous multi-threading processor. It's not because it's not a good idea. It's just because only Intel can do that. Okay, so after telling you the story about simultaneous multi-threading, can you go through this question and tell me what's your thoughts about simultaneous multi-threading and why do you think it would help? How many of the following about simultaneous multi-threading are correct? All right, wrap up in 15 seconds. 5, 4, okay, everyone voted, and look at the result. Well, C and D, they are popular answers, and sometimes maybe the 3 that you guys pick are different from the other 2 other people are thinking. So I think it's definitely worth a while for you guys to discuss with your friend for maybe 2 minutes. Go ahead, do it. All right, that's wrapping up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so after discussion, well, at least we are converging to C and D. However, C or D, right? So I do want to invite some of you to express as a representative of your group and tell me, what do you guys think? Okay, so I have Byron. Looks like we have a different start every day. So you are the star of today. What do you think?
So our group was thinking 2 and 3 are definitely true, but we're trying to figure out
Okay,
if 4 is true.
so
We're between
2, improve the throughput of a single threaded application.
Yeah, this is true
So
because
what's the concept of simultaneous multi-threading?
you're running multiple threads at the same time.
You're running multiple threads at the same time. Where are they running?
In the same, they get issued. Well, they're getting decoded and issued to the same, I guess, process or area.
Pipeline, right?
Pipeline. Yeah.
So do you think for a single threaded application, the throughput is going to be better or worse?
Oh wait, I guess if we're only running one application, then the throughput would be the same.
If you are only running one application, the throughput will be the same. And in fact, if you are running 2 threads at the same time, each thread, because you have to compete for resource, right, would do worse.
Oh.
Right? Okay. Right. Do you agree with that?
Okay.
So this is not correct.
I guess that's
right.
Oh,
how about the third one?
Well, I think that was like one of the motivations behind SMTs. So that's one.
Right. So if you have a cache miss, right, you can just schedule instructions on the other threads. Right. What else?
So for 4, we were thinking, so with superscalar processors, you could, or like it's still heavily affected by cache misses, but if we're running multiple applications at the same time, you may be able to have higher cache misses, which will like extend the time of per application, but because you're increasing the throughput, or not the throughput, but the number of applications running at the same time, you can afford that higher cache miss.
Yeah, because so the thing is that the cache miss rate may be higher because you have to share your resource with another thread as well, right? Right, so this one should be correct. How about the first one?
We don't think so because the speculative execution, those are also going to run into like competition with registers.
Yeah, but on the other hand, can you think about this problem in this way? So when I have a branch prediction, right, that I can potentially fetch fetch instruction from another thread. And the number of instructions that are mispredicted would be fewer in SMT processor because the process, or say the thread who is having the speculative execution mode, may have fewer instruction that you need to flush because you also will make progress on this, right?
Okay, that makes sense. Yeah.
Right. So the thing is that for the first statement, because you can fetch instruction from the other one. For the second part, you are going to hurt. For the third part, the third statement, again, right? And 4, because you are also sharing the cache. So I would say 3 of them will be correct. Do you agree with me now?
Yes, I do.
Okay. Okay. We can move forward. And thanks, Byron. So here's a summary of SMT. It proves the throughput of execution. However, because you are sharing your resource with others, so your single thread performance may be worse. And because you are also sharing your resource and pipeline with others, so when you have a branch misprediction, the progress that you made, the incorrect progress that you made may be fewer, right? So that's why, so the wrong path that you are executing is shorter. So the penalty is smaller, right? And it also increases the hardware utilization, and that's the whole purpose of SMT. And you only need to duplicate the PC and register file to support SMT. So that's why Intel processors and AMD Ryzen processors, they all support SMT. So, however, SMT is essentially just like a superscalar processor. And as you can see, the issue logic, it needs a dynamic scheduling. And this dynamic scheduling can be very, very complex. And the other issue with that is the power consumption. So before we talk about the power consumption issue of modern processor, why don't you just show me your understanding about power and energy through this question real quick? Okay, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so wow, I definitely want to show you this result because it looks like C, D, E, they all have equally amount of advocators. So I send a question out. Why don't you discuss with your friends within 2 minutes and let me know what do you guys think? So why don't you, well, sorry, I think I muted myself. So after discussion, looks like D and E, they are both popular answers. At least at least C is not the most popular now. So can I have some of you raise your hand, explain what do you think or your group thinks? Okay, Byron, thanks for saving us from the silence.
Yeah. So we all thought E was true.
So everything is true.
Yes.
Okay. So, okay, so do you mind to walk through
Sure.
the concept with me a little bit? So what is power?
So power is the amount of energy you use over time. So I guess like, I don't know, joules per second or something.
Actually, you flip it. Energy is the amount of power that you used over time.
Oh, okay.
So if you look at the definition of energy is power times time, right? And power, it means that within a period of time, within this moment, how much electricity has been drained, has been consumed, and and when you consume electricity, it generates heat, right? So that's power. And energy is how much power you drained, the aggregated power you drain over time. That's energy, right? So when we count electricity bill, when we count battery life, because battery is the storage of energy, it's more related to energy consumption. And lower power doesn't necessarily mean better battery life. If you make the processor slowing down your application too much, right? So if you look at this definition again, how does that change your mind?
So yeah, so lowering the power consumption doesn't necessarily extend battery life.
Right.
But it definitely does reduce the heat generation.
Right.
And lowering the energy consumption does reduce the electricity bill.
Right.
And then
the fourth one is still correct, right? But
yeah,
actually, why do you think the fourth one is still correct?
I kind of read it somewhere, so I kind of forgot why.
Okay. Okay. So let me.
Why.
Okay. Let's look at that together, right? So if you remember your reading in the textbook, it will mention that the power consumption has two parts. One is called dynamic active power. It means the power consumption because you are switching the transistor states. And the dynamic power is calculated in this way. It's alpha means the average switches per cycle. C is the capacitance of your circuit. So the more transistors you have, the C is going to be. The means the supply voltage of your circuit. And the frequency is the clock rate of your design. And usually it's a linear with voltage. So if you were if you were enthusiastic about like hardware, you know, like whenever you need to overclock your processor, the consequences is that your supply voltage needs to go higher. And N is the number of transistors. So, oh, sorry, this is the capacitance per transistor. So N is the number of transistors. So that's the dynamic power. So this part is related to the frequency of your processor. However, there's also another part of power called static leakage power. And this is because it causes leakage power because our circuits are not perfect. So even though you are not doing anything with your circuits, whenever you have it connected to a power, whenever you give it a supply voltage, it will drain, it will start to leak electrons from your capacity, like your transistors. That's leakage power, right? And if you look at the breakdown of figure that you have in your textbook, you'll figure out like in 20 nanometer process technology, and right now your processor is generally at like 14 nanometer or 10 nanometer or even lower. And for those process technology, you will see that half of the power is in dynamic, half of the power is in leakage, right? So in this case, it means that even though I'm not doing anything, half of the power will be gone because of the leakage power. All right. So do you agree with that? Answer is 3 now.
Yeah, so because of the leakage, it's still using a significant amount of power, even when it's not
right
10% of its utilization.
Right. Okay. Thank you. It's very good. So let's look at that, right? So power is actually a huge issue right now, because if you look at the power density of our processor, it's actually as hot as the sun now. So so how do we and the power consumption is actually creating a lot of issues. So we definitely want to lower the power consumption. And part of the power, half of the power consumption goes into dynamic power. And if you look at the function of dynamic power, how it is calculated, is actually have a cubic relationship with your frequency. So right now, I want you to think about, if I double the clock rate and double the number of cores, and I can make the program parallelize, and both solution would give the same speed up. Which one would, by how much more energy the processor running at a higher clock rate would consume? Meaning that doubling the clock rate versus doubling the number of cores, how much power of the higher clock rate processor would consume over the other one. All right, let's wrap up in 15 seconds. 5, 4, 3, 2, 1. Time is up. Okay, so looks like, well, most of you think is C, meaning that's the same. Is that really the truth? So right now, I just, let me do this. Oops. Okay, come on. Okay, just send it out. Okay, so right now I am just sending out the screenshot of the question, and I encourage you guys to discuss with your group, and whenever you are done, just go back to the main lobby, and so that I know you guys are done with your discussion, so we don't waste time. Go. So wrap up in 15 seconds. Okay, time is up. Okay, so can some of you share why do you guys think the energy consumption will be the same for both? So from the voting result, looks like A and E, they are the least popular. Okay, Japon, what do you think?
Okay. I think from the textbook, the frequency is linear with power consumption.
No.
Uh,
The frequency is linear with power consumption, but frequency is also a function of voltage, right? So if you want to raise the power consumption, if you want to raise your frequency, you have to raise voltage.
then it will actually be quadrupling the power.
Yeah. So then in this way, what's the answer now?
2.
2. Are you sure? Okay. So let me walk through this. But thanks for your comments. Okay. So let's just give you an example, and I would use this example to show you like how everything connected together throughout the very beginning of the class and the very end of the class. So in the very beginning, we talk about speed up. So let's say this example, right? It gives you an idea like if I can double the CPU frequency, then I get a speed up of 1.24. And this is exactly an example that we had before. So if you look at the power consumption of the new design, which is the double the clock rate, the power consumption is the cubic relationship with your frequency. And if you double the clock rate, you are going to consume 8 times more power. And speed up is 1.28, and the energy is the power times execution time. So the new power times the new execution time is equivalent to the old execution time divided by the speed up. So you will get the result that, wow, the power consumption is 6.4 times more than the energy consumption is 6.4 times more than the baseline. However, if we use MDOS law to conduct the speed up for multi-core architecture, and previously we have this function, the speed up of parallel is actually 1/1 minus F parallelizable and F parallelizable divided by N, right? And let's say like if I double the number of cores and the power consumption would be twice because I'm getting twice the amount of transistors, right? And if I assume only 40% of my code can be parallelized, and even just with 40% of the parallelization part, it will also give you 1.24 times performance, 25 times performance. And if you put that into the energy equation, you'll figure out it only make the energy consumption 1.6 times more, which is 4 times better than the doubling the clock rate. So that's why the answer of this question is actually E, 4. And this also gives you a reason why chip multiprocessor, meaning that putting more cores within a processor is more popular nowadays because it's going to help us reduce the dynamic power consumption in your processor. And as you can see, right now, almost every processor, they are multi-core, and server processor like this one, it has like 24 cores and it says 48 threads. That's because you have the simultaneous multi-threading to present a front end of 2 threads for each core. And another thing you can see is that for processor with more cores, the frequency is actually lower. So for these processors, they are all at the same technology. As you can see here, 40 nanometer, and they all launch at the same date. So they are the same generation. However, if you have fewer cores, you can run at higher frequency because, again, the power budget of your heat dissipation is limited. And the higher the frequency, the harder the power you have. So if you really, so if you want to have high performance, instead of keep boosting your clock rate, you have to instead make processor that are slower but with more. So that's also because of the limitation of power. And if you look at the design of modern processor like Intel Sandy Bridge is an 8-core processor, and for AMD processor, it's also a multi-core processor. So the concept of chip multiprocessor is actually we duplicate cores, and each core would have its own L1, L2 cache, and connected together or synchronize their data through the last level cache. So we will talk about more concept about simultaneous multi-threading later. However, chip multiprocessor in the next lecture. But before you leave the classroom or leave the lectures, a few things that I want to let you know. So if you have done your cave, don't forget to take a screenshot and fill the survey. And this will count as a full credit assignment, and because we are dropping your lowest 2 assignments now. And it also means that we make assignment 5 kind of optional, but you can still turn in it and we will still grade it. And but you are strongly encouraged to work on assignment 5 because it's considered as because it's like a mini final. It covers a lot of important aspects of the final exam. And regarding the final exam, try out the lockdown browser. I know some of you having issues with that, but so that's why we want you to try first. And if you really, really have issues with the lockdown browser, I'm still considering if we have to use the lockdown browser, because that's actually a suggestion that I got, and some people in the department is asking me to try out so that later on they can see if this is a good idea. And we are kind of like a pioneering class to support to test that feature. However, I know there might be issues with that, and nobody has tried that before. So that's why I create this like test quizzes. And if you figure out that, well, if we figure out that it's not going to work, I may have to change our final exam format a little bit. Well, it's still going to be the same time. It's still going to be consecutive nonstop 3-hour slot that you pick. However, I might have to change the question set a little bit to make sure that it's not easy to for you guys to work together, or at least if you work together, there will be an obvious sign that you have done that together. Other than that, I think that's everything I need to say. I will see you tomorrow.